Okay. I'm going to use two connections here, one for just showing you things, and also I'll be drawing little things. I have another camera here that this setup is a little bit, so I will be able to draw things. Does it work? Yeah, okay. So on this piece of paper, I will be drawing things, and I will be using the other connection for sharing screen. And there's a couple of ways to do a talk like this. One is just show and tell, and it's basically a talking head and a bunch of slides. PowerPoint thing is, and it's basically, guys, don't try this at home. These are, professionals doing it, and usually people complain that there's the barrier to come and join participating at a talk like this does not do any good. So what I'm gonna do is more of a kids, please do try this at home things. If any of the attendees want to play along, and I'm going too fast, or you're trying to do something and it doesn't work the same for you as what I'm showing on my screen, then just interrupt me. Or if you just have a question and taking notes and you want to do this, tonight yourself after we've done the workshop, and you just want to do it after, again, just stop me and ask me, hey, where did you clone that piece from? How did you do that? Yeah, just unmute yourself and don't be shy to ask these questions. So what I'm going to be talking about is external debug, because we know what internal debug is. And internal debug is, let's say you have some kind of user space software, and you're trying to understand what's going on, and you put a breakpoint, and GDB plants a trap instruction, and when you run and get to the trap instruction, somewhere the execution unit, so the trap instruction gets decoded, that, okay, we know this is a trap, and the execution unit says, oh, okay, it's a trap, and we're pulling on a line, and the processor gets a trap interrupt, and that interrupt goes through the operating system's interrupt gate, and the ptrace interface in the Linux kernel or in the AIX kernel says, oh, okay, so we have this ptrap syscall, and we report this back on the ptrace interface. We report this back to GDB, and that's how you do normal user level debugging. Things are much worse when you are trying to debug when you don't have a working operating system, or maybe you have an operating system, but the chip itself is malfunctioning, or something in the operating system itself, in the ptrace itself doesn't work, or you don't have this vertical, you don't have this horizontal nice layers of abstraction that Professor Feng was showing. And later tonight, I will talk about why this is critically important, that in this decade, everything is changing because you are participating at a level where basically nothing works. You cannot trust anything, and you cannot just say, well, okay, I am doing this application level, or I'm doing this compiler or something, because you are at this forefront of things where basically nothing works. So you're debugging vertically, and you cannot really you cannot really just say, okay, well, this level under me is given, and that other level under me is given, and the other level under me is given to me, and they work, and I'm just debugging my level. Uh, you essentially can only assume that nothing works. So what you do is now you need uh, this external circuitry that you instrument your processor and then, well, all of your system with. And the way how you normally do this, let me actually draw this. So I'm gonna switch to this camera so I can draw things. So this is your, so here's an external debug circuit. So you have GDB on top, and this is your debugger that normally would talk to a ptrace through ptrace syscalls in the circuit. What you do instead is you talk on you connect on a socket to some kind of RSP stub, what we call. So here's the stub, and what you talk on here is something you call RSP, for remote serial protocol. And these are packets that when you are trying to, for example, single step an instruction, so you send a packet, it's just ASCII. So your packet might look something like little s, and that single steps. So that is the step instruction command to GDB, and that results in an S packet, and now you are at the next instruction. Or what else? You could inspect memory, or for example, you want to inspect all of your registers. So you send this G packet, and the stub sends you on this socket just an ASCII thing, it just says, I don't know, FFFF0000, and then right next to it, this is going to be your register 1, and then register 2, and somewhere towards the end is going to be your exceptions and flags and program counter and all that. And this is this is all of the values what is in your registers. And you can go continue, and it will run until it runs into a trap or some kind of exception, so it stops. Now, the stub, what you do with the stub is that you have to somehow actually connect this to your running system. So for example, if you have this RTL board, so you have this FTDI chip here, which on the one side connects to USB, and then on this other side, it has two GPIO interfaces. One you configure for your console, so this is your UART, and the other one gives you some JTAG pins. So in here, the stub is talking to some library that provides you with some kind of JTAG connectivity, so that the stub is gonna be linked to something like URJTAG, for example, in our case. And what that does, it's a library that just does JTAG things, And this guy will connect to libftdi. And this libftdi, what it's going to do is going to connect over USB to the FTDI chip. And then this will go to your, well, this is some USB controller in here you're going to have in your workstation computer. And then you will have this USB wire, and this is going to connect to the FTDI 232. So this first two is that there is like two halves of them, and this guy is gonna go and talk to the debug circuitry. So there is gonna be some kind of interface between this guy and the actual debug module in the processor, and the debug module is going to connect to the execution unit, like, you know, the fixed point unit in the processor, and then to the decode stage, and then to the fetch, and so on. So you have things like, what is the current instruction, what is my current program counter, what is, and so on. And the tragedy of what we had before in the power ecosystem would be that there are very, very nice, from a functional perspective, very nice circuits in normal implementations of power. The problem is you need some kind of hardware. So if you're using, let me show you some traditional hardware here. So if you're using some kind of, what is the one that oh, there, sorry, I have it. So the traditional one, the oldest one, is IBM RISC-Watch, and I don't know where mine is in the pile of machines in the basement, all kinds of RS6000s and a bunch of boards and whatever. But I have something that I have loved for a long time. This one was made by a company in Switzerland, and it's fast, it's functional, you love it, can take a lot of abuse. The problem is the company that made this, they are no longer there, and you need software to drive this guy. This is a GDB. You see, you connect this to a network, and this is where RSP protocol travels over TCP/IP, and this one you connect to your target, and it's all fine, but you're trying to use it, and you say, oh, well, this thing needs internal firmware to be loaded that is specific to your PowerPC implementation or whatever processor you're using, MIPS, ARM, and you cannot get it, even though you paid, I don't know, $5,000 for this device. You cannot get it because the company's website no longer exists, and you lost your collection of things, or you want to do a different processor and you want to get another firmware, and it does not exist. And you have many kinds of this. You used to have this one. This is kind of similar from Freescale, and they don't do power anymore. They don't want you to do power anymore because they have their own agenda. and this one is McGregor one. So what you do is you may want to try to reverse engineer the protocol. You connect the McGregor to some kind of thing where you, I don't know if you can see on the camera, it's basically you just piggyback in the middle and you continue between the McGregor, and you continue here and you hook up a logic analyzer here, and can take you months and months just trying to get these things work. And there has been some success. Some public organizations have figured out how to do this in an open way with various degrees of success. But that none of that really matters. What you want to do instead is we have a fully open implementation of power, which is microwatt. This is ours, and you just implement your own protocol for debugging in your own hardware and your own software. So you can have support for it in open source tool chains, for example, in GDB, because in GDB or in OpenOCD or in tools like that, you don't have support, you don't have support for this, 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 because NDAs and all that. Now, in microwatt, initially, how we have it before we started looking at this, there is already a somewhat minimal support for this new protocol, which we call DMI, the debug module interface. So the DMI, it sits, let me draw again what happened here. Does it work? Okay, so that sits here. It's part, so this is your debug module interface. So this is the debug module, and this is the DMI that sits between this JTAG protocol, and these are just some wires inside microwatt. So this is the FPGA here, and here you have the actual interesting things inside microwatt. So this is FPGAs, the FPGA boundaries here, and you're implementing microwatt here. So this is inside, or the VHDL code for this is inside the microwatt repository. And there is a minimal interface that there is a couple of JTAG instructions that you shift in, and you get things like start, stop, instruction cache reset, continue, get me registers, some trace capability, but there isn't really advanced stuff like hardware breakpoint on any of this, and by any of this I mean a mask plus an address for instruction, or address plus mask for data, or like data address, or for data value. If I'm there's none of that, and you would think that you really need much more than this to do actual interesting debugging, and that is that is just not true. And I will show you what we did. We did a hackathon session a few weeks ago with Jan and a bunch of other guys, and it is actually possible to connect fully blown GDB and have breakpoints. And I'll show you, if time permits, also even connecting GUI debugging tools such as Eclipse CDT plugin, and have a full interface with anything you can dream about, just given this minimal number of external debug facilities implemented in actual microwatt hardware that it already has there. So not to be just a talking head, I'll give, especially for the sake of the student attendees, I will, or at least trying to share my screen on the other channel here. So let me see if I can share screen here. Yeah, the whole desktop. I hope this is gonna share. I don't know if can you see my actual screen?
Yeah, I can see
okay.
something.
So yeah, right. So I have so I have two black consoles, like bash terminals, and we're gonna take this RT, because I believe this is what the students have, and we will just do a little lab. And who wants to follow, you can follow. And if you want to do it after, you can do it after. But if you want to do it now, you can even just follow now. So on the computer screen that I'm sharing. So here, the first thing you need is you need to clone the microwatt thing. I'm assuming that you have RT and you have some kind of Vivado license. And the first thing you need is this repo from Anton. Current head of master is okay. So we just, I'm gonna kind of skip a little bit forward this first step. If you are interested in microwatt, I would assume that you probably have this already, and synthesize the core, and you have something to put on your RT, or you had something. If not, you can interrupt me, and we will slow down. And it's just that the synthesis phase is a little bit, it takes time to synthesize the whole core. But basically, what you in here, this is your, if this is a clone at master, and this is just that repo. So you clone that, and then you go and create where you are gonna where you're gonna build things, and you just do your normal fuse sock build. Uh, it takes about 20 minutes to do, so I have a pre-built thing, and then you flash it onto onto the RTL. There is a script for doing that, and you just take it's in here, and I recently let me show you a little bit. So you just give it uh, where in the QSPI flash chip to put which FPGA you use, what kind of file it is, which cable to use, and what that does is it configures the FPGA for a proxy to put the bit stream into the flash chip, and then when you reprogram the chip from the flash, that's going to be now, instead of the proxy, the A35 or the A100 or whatever your RTX the part is on the board, is going to be actually programmed with the actual microwatt gateware. So you go something like I have an A100, and well, this one is the one where I did the U-boot. So what we're gonna do is we're gonna take our directory where we built the gateware. So this is the build, and then there, and then RT, and then I have dot bit, and that is going to flash the gateware. And let's use when we have that in the flash. Let me use this other. Actually, I like color coding my consoles, so we're gonna take a third one, and let's color code it like this amber thing on the right, if you can see. And I'm gonna why USB 1 is the second channel on the FTDI. With the first channel is the JTAG connection. The second channel is the UART. So the speed is this, and it has its own. The FTDI powers from the USB. So now I'm gonna press on that, and we have a microwatt, and I have some residual U-boot in there, but let's go in there. So how do you debug a running thing? So the next step, we would like to get a U-boot and compile it and flash it right after the gateware and jump to it and debug it. So what you need is U-boot from here, not any which, because the upstream does not have everything, I believe. So you can take Shenki's U-boot, or you can take mine. It is the same. Take the microwatt branch, and actually let's do it from the very beginning. So no, not here. I'm gonna blow it away. So RM minus RF U-boot, and I'll show you. So we git clone this guy. So paste the repo here, and oh yeah, there's a very long history, so it's gonna be a little bit slow even on a good connection. Maybe it was not the best thing, but we're gonna configure that for the microwatt processor. We're gonna build that. In order to do that, you need the a 64-bit PowerPC GCC for Little Endian, and in your in your Linux distro, they are usually prepackaged. Ubuntu, Debian, Fedora, they all come with prepackaged Power GCC, so this should be easy. Okay, so here is, we go to U-boot, and we are on master. We don't want that, so git checkout microwatt. Okay, now I'm on microwatt, and the first thing I want to do is I want to make the config. So what I do is I need to pass it what my cross-compile toolchain is. The arch is PowerPC. O equals is where to put the build artifacts. So this stuff here is the build directory. And now this is the config to build. Right. So now I have this .config, which is going to be the config file. And then I am simply going to make same thing, but without the dev config. It's just build. And this builds. So not here, but in build, because I said -o equals build. So I go to my build artifacts, and the file uboot is the elf. So file uboot Little Endian PowerPC 64-bit, right? So that's my U-boot, and I go and flash it. So that is A100, say -T. This is gonna, so 40,0,0,0,0 is how big my gateware is, starting from 0 in the flash chip, and this is I'm writing it right after the gateware, and then the first stage bootloader is gonna jump to this offset in flash. So we're flashing this. And then I don't really have to reprogram the FPGA. It's enough to just restart it. So and here I just pressed a key, so we stop the auto boot sequence. And now we have something running. So let me show you the little, actually not really the little one. I'll show you the real thing. So this is a RSP stub that Jan wrote in the course of the weekend, and it is a very tiny RSP to JTAG bridge. So basically what happens is, this is a Python program. We have many different implementations. We have seen there's one in Gem 5, there's one in OpenOCD, and it is so simple that it really is not a long exercise to write another one in Python. So what it does is, so this would be your GDB. And here's a TCP socket. So say TCP on port 7000. And this guy, the Pi GDB stub, it listens on the socket, and on the other end, it connects to this lib_urjtag, which has Python bindings. I can show you on the screen that in the microwatt Python, what we do is we are implementing here all these parts of the DMI interface. And all it does is just connecting to this. Let me show you the connect. Right. So board is RTL. This is all from the urjtag bindings for Python, and you just add part registers, and this is now the ID code is just the ID code of the FPGA part itself, and the interesting instruction is actually this, and we just shift getting the ID code first, and then our user2 instruction, and then the command is simply this user2, and then we set we set the data register in, and then we shift the instruction, and we shift the data, and then we shift out the result of the instruction, and then on top of that you have the DMI read, DMI write, and everything else. It's a little this DMI. It's an address space, and these are the addresses of things that happen here. See the NIA, is it here? MSR, is it there? The different commands that travel on this, and this is. Right. So what you do is when you read NIA, is you just do DMI read at that address inside the DMI address space. So that's as you can see, it's just one file of 369 lines. Now let me show you how much this actually gives you. So let's There's a little instruction about how to run this. Jan has automated most of this in a makefile that you just clone his repo. So let me do this. Let me show you in this one. So this PyGDB stub, that's his code. So git remote show, and you just take that. You run his script for installing this in a Python virtual environment, and you activate. So now I'm not in my global Python installation. So I'm gonna source is env beam, and the script is activate. This is standard Python virtual env stuff. So now I am in the PyGDB stub virtual env and have all of this available to me. And now I just run the stub. So minus m gdb stub microwatt on port, right? So the target is microwatt. Everything default, the default is RTL on the second half of the FTDI, and listen to port 7000. So if I just run this, now it's just sitting there listening on port 7000. Now, we forgot to do something. I forgot to show you. Boot. In the makefile, I want to change something. I want to change this to debug flags. So I'm gonna not optimize and minus ggdb. So to get all the symbols and all the dwarf information into the binary. So let's redo this. So I'm gonna remake this, and I'm gonna flash RT to that. Right, because otherwise I'm not gonna have symbols. And with symbols, I'm gonna show you a little bit of a, let's get rid of this for now. Okay, so that's programmed. I'm gonna restart this again, and I am okay. Well, so I'm now ready to connect and do external debugging here. So this is now listening to port 7000. And what I'm going to do is I'm going to go into the U-boot directory. Here's my file. No, build. Here's my file. And I'm going to GDB on that thing. U-boot. So, so it read the symbols from the ELF and understood that this is, well, some kind of 64-bit PowerPC. All right, now I'm gonna connect over RSP from this guy to this guy. So actually, to see, well, let's just connect, and maybe if you're interested, I will show you the packets. target remote localhost port, we said 7000. And now I am connected there, and this looks like the correct kind of meaningful program counter, but I'm even getting some sort of backtrace, but I'm not getting any source. And the reason is we're really getting out of the topic of DMI itself now, into more into the questions of realities of real life debugging. One hurdle is that this is U-boot, and we are already somewhere, like we are running here, right? And what U-boot does before actually starting to do anything is it relocates itself, in this case, from the flash to DRAM, and the addresses that are given by the linker, well, they are not, their addresses in flash, but now U-boot is actually running not out of the flash, but it has relocated itself to RAM. So this is an address in DRAM, and the addresses inside the symbol table in U-boot, these are addresses in the flash. So we know how it does it. There is this global data struct, and it has offsets, and it has the addresses before relocation and addresses after the relocation, and the offset between the two. So what was it? Wait. Oh, because I'm stopped. Okay. Nah, I'm gonna continue for now. And this immediately worked. BD info, so board info structure. So BD info. And that no, it's somewhere. Relocation offset is this. I hope you can see when I am selecting things. So let's stop this, and I am somewhere, but again, it doesn't know. So in order to get the correct symbol table, I'm gonna get rid of the current symbols. So symbol file, and give it no arguments. So I want to discard this guy. Yes. No symbol file now. And then add symbol file U-boot and -O for offset hex 3F6. How is it? 3F6 D000. With all sections offset by that. Yes. And now I backtrace. Aha! These are all my symbols. And I can do, I can set breakpoints. I can set, now about breakpoints. There's no hardware ability to set breakpoints right now, but GDB supports a very wide range of possibilities. If the board supports hardware breakpoints, that's great. If it tries to set a hardware breakpoint and it says, I cannot, so it tries to set a trap. Well, on this here, a trap on the current gateware in microwatt, a trap, what it will cause an interrupt at the trap vector. And there's no software to actually do that. What we want to do is an actual honest to God stop, or something that will cause us to be able to see where we stopped without any systems software, because we don't have any yet. How do we do that? Well, the stub, when it tries to receive a packet telling it to plant a trap, it says empty response. So GDB knows that, ooh, that stub is not just stupid, is really, really stupid. Now I am gonna plant a breakpoint instruction. And the stub knows let me show you where it does it. In microwatt, I believe. Let me find it. Hang on, this is it in this? There is, yeah, software break instruction. And in this case, let me just grab for it. It's in
the software break instruction is in the microwatt. This is a generic code for all targets.
We just look at it though, right? Like, where is it? Break.
Yes, on the bottom of this file.
At the bottom, okay.
At the bottom. Yes, there is.
Oh, yes, 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 yes. And look at this. This is 480000. So what this is unconditional branch to offset 0, right? Not branch absolute, branch relative to 0. So it just loops, and the stub sits in a tight loop looking at what is my program counter. And if it is what I wanted for a breakpoint, oh, okay, I will stop the core, because the gateware, well, doesn't know how to compare addresses yet, but it does know how to stop. And this is pretty standard what you do in like really, really prototypical early stage debugging. And GDB has been using this kind of tricks forever, and it works really well. I mean, you can plant a breakpoint in whatever you want. I can break what? Let's say let me go here so I can see what I'm doing, right? So this, we were talking about this BD info, right? So I want to see how BD info is implemented. So I think the is do BD info is the name of the function, and we just set a breakpoint there in that file, and let's say I continue. So obviously this does nothing for now, but if I go BD info and I go here, well, now I am stopped at the breakpoint, and I can list, and obviously I have stopped, so nothing happens on my console on the right. But again, I can look around, I can step in things, and if I continue again, well, oh, okay, well, that we're gonna see. Okay, we're gonna see it. We're gonna need to investigate why this didn't quite continue. Oh, okay, something catastrophic happened. Right. So, right, sometimes things don't go quite as planned. How are we doing on time?
See, Boris, we have the other speaker join. So let us have Mark to present, and then you can continue. You can resume.
Right. Absolutely. So is time for this intermediate presentation, and then there is my other stuff. Okay.
Yeah, you can continue the same thing, and then the other thing also. Yeah, this is all good.
Okay, perfect.
Thanks for the very interactive, the talk. I really appreciate it, and we will resume our presentation after Mark's presentation. Thank you, Boris.
Yeah.